Okay, so am I audible?
Yes, yes, you are.
Okay. Should I
So,
start and
yes,
try to
yes,
share?
yes. We
Okay,
can start.
okay. So I will try to share screen now. Ah, So is my tab visible to others?
Yes, it's visible to me. It should be visible to the participants. Yes, yeah.
Okay. Uh, okay, so let me try and continue the discussions we were having yesterday, and then maybe if there are any questions, we'll take it, maybe a little bit into the discussion. So if you remember, we were trying to, towards the end of yesterday, discuss about beta decay, and here it is. So, and then we tried to build some effective theory of beta decay, which is known as the Fermi four fermion theory, and we discussed its success and why it cannot actually be an UV complete theory of beta decay because it violates unitarity at some scale, right? That was our discussion. But let me go back and point out some more experimental inputs from beta decay itself. Okay, so one of them, which we already kind of mentioned earlier on, is this is I couldn't say it's really a experimental input per se, but at that point of time when in the 1960s and 70s when the standard model was being built was actually an experimental fact, but now of course facts are in science are not really a time independent quantity. So the experimental evidence is pointed to neutrinos being massless, so we can say that as one of the important ingredient at that point of time. And then let me uh, continue this discussion um, with another important aspect, which is what we call parity violation. Okay, so again, we are still at the stage when from experiments we are trying to identify uh, the properties of the particles and that participate in weak interaction and the nature of weak interaction. Okay, so that we can then build a gauge theory of weak interaction. So the next important input about uh, weak interaction is that parity is violated, and the most important, I think, experiment is parity violation uh, in beta decay. And this was actually done by several people, but also in Wu's experiment, which is a very famous experiment. It was very surprising because till then all kind of fundamental processes or natural processes that people saw, which were mostly processes involving electromagnetic interactions or strong interactions like decays of mesons, hadrons, or simple interaction between charged particles. Parity seemed to be an sacrosanct quantity, a member of the Poincare group, which is always preserved, and there was no reason to believe that parity can be violated. But then there was this experiment, and let me try to briefly explain this experiment, without going into any details. So the idea was that you take this, let's say, cobalt nuclei, and then you try to align the magnetic moment of that nuclei using some kind of an external magnetic field. Okay, so just assume that this is, I don't know, a cobalt nuclei, and this is the magnetic magnetic moment of that cobalt nuclei, which has been aligned in a particular direction due to some kind of an external magnetic field. Okay. And let's say that this is undergoing a beta decay. So if you remember, the beta decay process is, of course, the cobalt transforming to nickel and an electron coming out. Of course, along with it, there is a neutrino. But in typical experiments, you cannot detect this neutrino, at least at those times. You cannot detect the neutrino. So that is an invisible thing. So basically, you see the electron coming out. So let's say you see the electron coming out in a particular direction. Okay, something like this. So if you think about this, the parity transformation of this entire story would be, let's say this is the, okay, what did I do? Yes. So again, this is the parity transformed nucleus, again aligned by the same magnetic field. Remember, the angular momentum direction do not transform under parity because it is R cross V. It's angular momentum, right? So under parity, R is transformed, V is transformed, but R cross V is still pointing in the same direction. So J still points in the same direction, but the electron, the momentum of the electron will now point in the opposite direction, right? So it will now point somewhere like this. So this is kind of the parity transformation of this thing. Okay. So this is the electron, and this is the parity transformed version of the experiment. So if the left-hand side is the electron coming out in the original setup, then the parity transformed guy would be the other one. And then if you have detectors which are placed everywhere around this nucleus, let's say you have a detector here and you have a detector over here, then if parity was actually conserved in this beta decay process, you would see the same number of events in these angular directions. And in this Wu experiment, what was expected is that if you had detectors all around this cobalt nucleus, you would see the same amount of electron in every direction. And unfortunately, it was found that there is an asymmetry in the angular distribution of electrons coming out from this cobalt, which kind of showed that parity is not conserved. Okay, so that was the upshot of this Wu experiment, that parity is not conserved in beta decay. So this was the first evidence that in weak interaction beta decay, beta decay parity is not conserved. But very soon other evidences from experiment piled up. For example, the famous theta tau paradox. So this is again a historic name, but the idea is very straightforward. So basically what it is that if you remember the decay of this K plus, I pointed this out at the beginning, that this K plus meson has a very large lifetime, 10 to the power minus 8 seconds compared to a typical strong resonance, which has lifetimes only of the order of 10 to the power minus 20 or even smaller, times. So this K plus usually decays through weak interaction, and it has two decay channels. One of them is this pi plus plus pi 0, and the other one is pi plus plus pi minus plus pi plus. Okay, so it has these two things. For historic reason, this is sometimes called the theta, and this was sometimes called the tau, because people thought they were two different particles, but they are basically still the K plus meson. And the problem was that if you look at the right hand side of it, the pi plus pi 0 and the pi plus pi minus pi plus, they have different parity configuration. Okay, so this decay, the first one is actually parity violating, and this one is parity conserving, because these two things have different parity configuration. So both of them cannot simultaneously be parity conserving if they are the decay of the same mother particle. So if K plus cannot simultaneously decay to both of these parity configurations. Okay, so the only way this can happen is if one of them is parity violating. So again, this was another proof that parity is not conserved in weak interactions. So this was another experimental input that we have to add to what we have learned so far in this study of beta decays, so that we can build a theory of weak interactions. So just like what we did for our strong interaction, I think it is now time to make a summary of what we have learned about the the particles and the fields that participate in weak interaction. Okay, so let's try to look at the and for now let's just look at the leptonic sector. Okay, so there are the quarks, but there are also the leptons. But for just to for our first introduction into this theory of weak interaction, we would just focus on the leptonic sector, and then we can extend it to the quark sector as well. Okay, so the properties of the leptonic, which means basically electron, electron neutrino, muon, muon neutrino, etc., particles and fields of weak interaction. So what are the properties? So the first thing that we can start with is this idea that parity is violated. So if parity is violated, then we already know that these things, this, let's say, if you start with the electron field, if you start with, let's say, the field corresponding to the electron, this electronic field, which is a spin half particle, can corresponding, can populate either the half zero or the zero half representations of the Lorentz group, right? And we learned previously that these two things are connected by parity. And when we were building the QCD Lagrangian, we chose the quark fields to be in a linear combination of them, just so that the QCD theory conserves parity. Now our mandate is to do the opposite. We want to make them violate parity. So our choice is obvious, that we want to choose this field to be such that it populates only one of these things, either half zero or zero half. And this is what was proposed originally by Sudarshan and Marshak, and separately by Feynman and Gell-Mann, that what you do is that to make this large parity violation, you assume that this electrons and everything, the weak interaction, only couples to one of these representations. Okay, this is called maximal parity violation. So you assume maximal parity violation, and you choose this E of X fields, or for all of them to be the left handed while fermion half zero. Okay, so this is how you would choose the field. But then there is one more subtlety. The subtlety is that this while fermion is a two-component fermion. Okay, but the way we usually learn things is that we are first introduced to the Dirac field, because we learn the Dirac equation and we are very comfortable with the gamma matrices and the Clifford algebra. We know how to take traces of the gamma matrices. We are less familiar with this two-component while fermion and taking traces and things like that. So it is sometimes, just at an operational level, to do mathematics, to do calculation, better to hide this two-component while fermion inside a four-dimensional Dirac body. Okay, so it is actually a two-component spinner, but we want to place this two-component spinner into a what would look like a four-component object. In that four-component, two of them will be redundant. They won't exist. Only two of them would be the valid two-component while spinner, and the other two will not, will just be placeholders. So this is called the chiral basis. And the way you do this is that you put this Ex as some kind of a psi El of X, which is written as 1 minus gamma 5 of 2, which is a projection operator of a Dirac field psi E of X. Okay. So let me just label what I have done. Remember, your original choice is that this is a while fermion half zero two component. Okay, but you put this inside a left chiral field which is projected out from a Dirac field using a projection operator called 1 minus gamma 5 by 2. So what is the idea over here is that every Dirac field that you have, so let me just point out, just take an aside to write this chiral decomposition. So every Dirac field that you have, let's say this is a Dirac field, you can always write it as 1 minus gamma 5 by 2 times psi x plus 1 plus gamma 5 by 2 into psi x. Okay, because I've done nothing. Okay, I've just written minus gamma 5 by 2 psi x plus gamma 5 by 2 psi x. So I've just added and subtracted the same thing, right? I shouldn't even write like this. I should just say equal. But this quantity over here can be written as psi L, and this quantity over here can be written as psi R. Now, why this is useful is because of the following thing, that the Dirac Lagrangian, which in terms of the full Dirac field is written like this, in terms of this psi L and psi R operator can be written, in the following form. So there's the separate kinetic term for psi L. There is a separate kinetic term for the psi R. And then the mass term is given by psi L bar psi R plus M psi R bar psi L. If you just use the known properties of psi gamma 5, which you must have studied from your discussions about the Dirac equation, you will be able to show that if you decompose any Dirac fermions into this psi L plus psi R, your Dirac Lagrangian gets decomposed in this way. Okay, and this is the advantage we want to use, because we want to still be able to use the known gamma matrices in our Lagrangian. But you must remember that inside this psi L and psi R, there are only two useful degrees of freedom, whereas in the psi, there are four useful degrees of freedom. Okay, so this has 4 degrees of freedom, this has 2 degrees of freedom, this has 2 degrees of freedom. And this basically comes from here. Okay, this was just a very quick comment about chiral decomposition, which is very essential in the weak interactions. So let me go back to our discussion. So to have maximal parity violation, what we will do is that we will take every field, the electron, we will, let's say, okay, let's not even write like this. Let's say for the electron, we will choose some kind of an electronic left-handed field, which will of course be in the half zero representation of the Lorentz group. Similarly, for nu E, we will invent some kind of a psi nu E L field, which will be also in the half zero representation of the Lorentz group. And then, of course, for mu, it's the same. I don't want to go on. And all of them will be just in the left-handed components only, and we will say that only the left-handed components weak interaction. Okay, so this will take care of the fact why parity is violated, because the right-handed component is not even participating in the weak interaction. So this is point number 1. That takes care of the first experimental input of parity violation. The second thing is what we discussed at the beginning, is that we discussed that, if you go back into our this Lagrangian, let's say over here, of the effective Lagrangian, 4 fermion Lagrangian, and if you look very carefully, you will see a very interesting thing. Let's say if you focus on the electron neutrino pair in this effective Lagrangian that you can see at the center of the screen, you will see that this electron and electron neutrino pair, they always show up as a pair. They always come in a pair, the electron and electron neutrino. Wherever they appear as a pair. Wherever they appear as a pair. Wherever they appear as a pair, right? In this Lagrangian. So it seems that this weak interaction kind of puts the electron and the electron neutrino on the same footing. They always appear together. So just like for the strong interaction, we assume that the 3 color varieties of the quark appeared in the same multiplet. It seems for the weak interaction, the electron and its corresponding neutrino, they are not different from each other. We know they are different because they have different charges and stuff, but for the weak interaction, it seems to be blind to everything and they seems to be similar. And so we would claim weak interaction puts the electron and the electron neutrino on same footing. I don't know what happened. So we will introduce now some, fields, the actual fields of, things which experience weak interaction as these doublets of mu e and e, mu mu and mu, and mu tau and tau. So there are actually three families of leptons. So the electron and the electron neutrino, they will appear together. The muon and the muon neutrino, they will appear together. And the tau neutrino, they will always appear together. And these are the things that are experiencing weak interaction, but only, as we discussed before, the left component of them. Now, what about the right components? So the right components, we go back and we look at this decomposition of this Lagrangian over here. You see, the right component, we cannot just wish them away. The right component remains important in the mass terms, right? A thing cannot get a mass, it seems, in this Lagrangian at least, if the right component do not exist. At least for Dirac fermions, this is true. A Dirac fermion, gets a Dirac-like mass only if both the left and the right components exist. So we know that in our, again, quote unquote experimental input was that electrons we know have mass, and we have assumed that the neutrinos do not have mass. So for the right component, we have to take this call that the right components are singlets, and we'll call them as EF, and they basically contains the ER, mu R, and tau R fields. But there is no neutrino ER, mu R, and tau R. These things do not exist. We are just cancelling them away. So only these things exist. The first row exists, the second row do not exist. Okay. So now we know what are the field contents that we have. The field contents is very clear. We have this left chiral doublets, and then we have this right chiral singlets. So we have to write down a local theory with this left chiral doublets and the right chiral singlets. So let's just write down the weak interactions. Of leptons, okay, from this theory. So we know the drill by now. First we have to write down the free theory. So the free theory is very simple. There is the left doublets. Remember, this capital L is a doublet. So it will have its own kinetic term. but it will have no mass term now, because remember, the left chiral part, this is the chiral theory now. So the chiral part is a doublet and the right-handed part is a singlet. So unlike in the QCD, where we wrote down something like a mass term, here we cannot write a mass term. Again, go back to this thing. If we want to write down the left and the right together, that is not an invariant quantity anymore, because the left is a doublet and the right is a singlet now. And a doublet and a singlet cannot make a singlet. So you cannot write any mass over here. You just can write a kinetic term with it, and you do it. Similarly, for the E, the right-handed part, you can write down, oh sorry, I am forgetting the gamma mu's, I am very sorry. You can write down another kinetic term. And that's all. You cannot write down the mass term, you cannot write down anything. This is the free theory, two kinetic terms for the left doublet and for the right doublet. And then, like before, you try to look for the symmetries of this theory. So what are the symmetries of this theory? One of the symmetries is, of course, that if you take a 2 cross 2 unitary matrix, which can be written as e to the power of I, the Pauli matrices sigma A, alpha A. So this is a constant 2 cross 2 matrix. And the other one is a e to the power of I theta, a constant phase. And then you make this following transformations. That you shift psi L to psi L prime by this U2 times psi L. Remember, psi L is a doublet, so you make this a constant 2 cross 2 unitary matrix shift of, or what I am saying psi L, there's no psi L, I have called them L, okay. Just, sorry. This L going to L prime, going to L, okay. And then this all F. By the way, there should be a sum over all F over here. And similarly, so this of course will keep the Lagrangian invariant because of the, because the unitary matrix will keep things invariant. I hope you know how to deal with it right now, by now. But in addition to this, we also find that if you shift this by a phase and also this, by a phase, under all these transformations, the Lagrangian remains invariant. So for the L part, there is this extra symmetry that if you transform it with a 2 cross 2 unitary matrix, the Lagrangian remains invariant. But in addition to it, there is this thing that if you separately make a phase transformation of L and a separate phase transformation for E, and these two phase transformations do not need to be the same for both. For the L, you can make a different phase transformation. For E, you can make a different phase transformation. But for all of them, the Lagrangian will still remain invariant, which tells us that this Lagrangian has an SU2 which only works on the left part. So we'll call it SU2L cross U1, and this works on both of them. So we'll not specify that it is only for L or E, some U1, and for, because this U1 can have a separate charge for L and a separate charge for E, we have to specify what that charge is. So we call that charge as Y. So we'll call it SU2L cross U1Y global symmetry. And now it is one step to write down the local theory. So what we want to do is that we want to just convert this u2 to be e to the power of I sigma a times alpha x, and this u1 to be e to the power of I theta x. So in order to do this, we know that now we have to invent two different derivatives. So what was d mu has to be now promoted to d mu, and there has to be two of them. One will be the d mu acting on the L part of it. This will have a d mu minus I. Now remember, L is charged under both SU2 and U1. So this covariant derivative should take care of both this SU2 and U1. And by now you have done this gauge theory again and again. So I'm pretty confident you will understand what I am writing. So I will go a bit quickly with this. So G2 is, let's say, the coupling constant or whatever the constant corresponding to the SU2 part of it times the generator of SU2, which are basically the Pauli matrices. And then you have to invent some kind of a vector field corresponding to this SU2 generators. Traditionally, they are called the W mu vector bosons. And then one more you have to invent for the U1 invariance on the L. So the coupling, let's say, call it G1. Now this guy, this L will have to have some charge under U1. So we don't know a priori what that charge is. So that charge, let's call it YL. And we have to fix this charge at some later stage. And a field, let's call it B mu. And similarly, you have to invent a d mu for the right part of it. The good thing here is that the right part has no charge under SU2 because it is a singlet of SU2. It only is charged under the U1Y. So it will have only one, covariant part, connection part, so to speak. So the connection part will come only from the abelian group, and this will be G1 times whatever it is charged under this abelian gauge group. Let's call it YR times B, right? And from our experience, and I don't want to waste any time with this weak interaction Lagrangian will now have this L bar I gamma mu d mu L L minus E, and of course there can be the three different families for electron, for muon, for tau, and EF bar I gamma mu dr mu EF sum over all this F. Here F is not flavor but family, remember this. And then for both B mu and W mu, you need to have the corresponding kinetic terms. So the W mu is a non-abelian gauge group, so you need to have the trace W mu nu A, W mu nu A, whereas the B mu is just an abelian group, so you don't need to worry. So you have the simple Lagrangian of this kind. And this is what you would have. And if you look into the details of the interactions that are there, and you can work this out if you want, you will certainly find an interaction between EL, mu EL, coupling to some combination of W mu1 plus minus W mu 2, by root 2. I leave it to you to figure this out. Going to, let's say, EL mu EL. So just from that Lagrangian, you should be able to find out, if you just put in the correct form of this, the Pauli matrices and omega 1, omega 2, omega 3. Remember here, these things, sorry, A goes from 1, 2, and 3 because there are 3 generators of SU2. So some combination of 1 and 2 may show up, and this is how it would probably look like. And this is basically what we were dealing with in our Fermi effective theory of E. We did not know that only the left-handed was there, but something like that, right? When we were doing the electron neutrino scattering. And if you now look at it very carefully, you know that this coupling is some G2, this coupling is also G2, and the propagator here is a propagator of a massless gauge boson. So this thing would go like G2 square by K square, and this is what you would want to match with the G Fermi by root 2. And this is what your naive expectation would be if you try to match the local gauge theory with your, pore Fermi interaction. But the problem again came from experiments that it was observed that if this is true, then at low energies, that means when K is very small, the G Fermi should vary very, very rapidly. Okay, so this would imply a large variation in G Fermi at small energies. And this was not observed experimentally. So the solution was proposed by Schwinger, and what he said is that probably what you have to do somehow is that you have to change this G Fermi by root 2. The matching has to come from something like G2 square by probably K square minus some M square. And if you are able to do this, then at very small K, at small energies, the M will become the dominant contribution and G Fermi will slowly become a constant. And there will not be much variation in G Fermi at low energies because it will slowly become G square by M square, right? So the solution to this problem was to make the gauge bosons, this is reminiscent of making the gauge bosons massive. But this was a huge problem. You might just say, okay, if that is the whole thing, why don't I just go up here and add a mass term to the gauge boson? Of course, other than the fact that you already have a problem of how to add a mass term for the electrons, you now seem to have a problem in trying to match with the Fermi theory and have a mass term for the gauge boson. So before we come to the mass term for the electron, let's first address this issue of how do we have a mass term for the gauge bosons. So what is the problem of having a mass term for the gauge bosons? So gauge boson masses, and unitarity. So this is a part that I would like all of you to pay a little bit attention, because some of the introductory text sometimes glosses over the discussion that I want to do right now. Okay? Because it's a slightly subtle discussion, which is sometimes postponed to a more advanced part, and therefore most introductory textbook, do not discuss this, and therefore, but I feel that it is better to discuss the this subtle issue at the beginning and not hide it. So what is the issue? So I would like to again come to the crux of the matter, which is that if any theory has to make sense, any quantum theory, like a quantum field theory, it has to be unitary, which means probabilities has to be conserved, which means that there cannot be any quantum transition probability which can predict more, which can be more than one. So predicted probability of any event or cannot be more than one. So if you think about the vector bosons, so the vector bosons are, basically spin one objects. They represent spin one objects. Okay. So they have 2j plus 1 degrees of freedom. If we assume, so they have basically 3 degrees of freedom. So spin at most, massless vector bosons have only 2 degrees of freedom. Massive vector bosons have 3 degrees of freedom. But they are represented in the field theory by something which is a 4 vector, which has, of course, 4 components: A0, A1, A2, and A3. Right? So unitarity requires that the if you consider each of them as some kind of a wave function, this each components of this vector field as wave function, then the mod of this wave function, the norm of this wave function, which should be given by A0 square plus A1 square plus A2 square plus A3 square, this thing should be less than 1, because probability, the norm, the mod of anything has to be less than 1, right? Whereas Lorentz invariance, which has nothing to do with this probability and unitarity, it has to do with the representation of A mu as a 4 vector of the Lorentz group, tells us that this A mu is such that A0 square minus A1 square plus A2 square plus A3 square is the norm of the vector. So these two things are not compatible with each other. The norm in one case is the scalar sum of the square of each components, and the other one has this, of course, typical Lorentz invariance quantity, which is A0 square. Of course, whatever is the signature of the metric you choose. I have chosen a specific metric, which is 1 minus 1 minus 1 minus 1. So the problem here is that you have a representation of the Lorentz group, which is 4, which has to be decomposed. Okay, so this representation, okay, let me just tell you that in terms of again, if you do not worry about this, but let me just tell you something, that the Lorentz group with fixed momentum is called the little group. And this is given by an SO3. And under SO3, this A mu has a representation of 4. But what you need to do, under this little group, you need this 4 representation to be decomposed into a 1 plus 3 representation. It is very clear. You need to separate out this 1 and 3, A0 and the A1, A2, A3, so to speak. So one of these 3 would represent the 3 spin 1 degree of freedom, and this 1 would represent the redundant degree of freedom, and this redundant degree of freedom is what sometimes called the gauge redundancy. So why I'm telling you all this is basically for you to know this, that the structure of the Poincare group plus unitarity is basically gauge invariance. So gauge invariance follows from Poincare invariance and unitarity. So my advice to all of you would be to pay more attention to Poincare invariance and unitarity in a theory than gauge invariance, because gauge invariance will follow automatically if you have these things. For example, if you think about the addition of a mass term to a theory, okay? So let's look at the abelian mass term. A typical theory, let me forget about everything else. Let's say I have a field A mu of x, which is an abelian vector field, and I define an F mu nu, which is del mu A nu minus del nu A mu. Then my free Lagrangian for this field, as you know, is just given by -1/4 F mu nu F mu nu. And you know that this is invariant under some gauge transformation. The issue usually comes is what happens if I add a mass term to this, like this. This is a mass term. This has gauge invariance. Now you might ask that does this mean that if I add this mass term, gauge invariance is lost? Not at all. You see, you can rewrite this entire thing in the following way. Where B is some auxiliary field. So if you write the Lagrangian like this, you can show that this thing is invariant under this gauge transformation, provided that this auxiliary field, that this new scalar field that you have introduced, also undergoes this kind of combined gauge transformation. Now you might say, oh, you have cheated. You have added a mass term for this vector field, and you still preserved gauge invariance. But what you had to do is that you had to add this new field called B to it, and only then you could preserve the gauge invariance. But that is not true, because if you check what is the equation of motion of this B field, it is just a Klein-Gordon equation, del mu plus alpha m square B is equal to 0, and del square plus alpha m square lambda is equal to 0. You can formally take alpha to 0, and the Klein-Gordon field B decouples, but theory remains gauge invariant. So why I'm writing this is that you see in you will find it written many places that the problem in adding and mass term is that you lose gauge invariance. But that is not true. If you add a mass term, you can still have gauge invariance. And this is what is known as the Stuckelberg mechanism. Okay. So what is the problem? There's no problem in the abelian case. You can just add a mass term to an abelian gauge field, and that will become massive. No issues. But if you go back, in our case, we needed to add a mass to this W boson, which is a non-abelian gauge field. So the question is, can we add a mass to a non-abelian gauge field? So we have to then ask non-abelian. Now it so happens that you can do a similar kind of a thing, a similar Stuckelberg mechanism for the non-abelian theory as well. So again, let's say you write down a non-abelian theory. So this is the kinetic term, and then you want to write down a mass term. So this is like the mass term for it, and then you have this W mu, and then you add something like you did previously, and you call it U inverse del mu U whole square, and then you have to add some more gauge fixing terms, which I'm not writing. And this U thing that I have introduced now is an exponential. It's written as an exponential of I G by this M. And you have to introduce one field for every non-abelian gauge field that you have, times the generator of whatever is the gauge group of that non-abelian gauge field. And voila, it's done. You can show that now your gauge bosons have mass, because when you square this, there will be a term m squared W mu, and your Lagrangian is invariant under the transformation, gauge transformation, which is given by W mu A plus the typical gauge transformation, okay, plus G F A B C W mu B T, okay, something like this. And simultaneously, of course, you have to transform each of these auxiliary fields to so gauge invariance is again not a problem. You can still achieve gauge invariance even in the non-abelian case. Then what is the issue? The issue, like always, comes with unitarity. The problem here is that in this case, Now what will happen is that because your gauge boson has become massive, the massive gauge boson has 3 degrees of freedom, unlike the massless gauge boson. The massless gauge boson has only 2 degrees of freedom corresponding to the two possible polarization states. Okay, left circular polarized or right circular polarized, like you see in your light experiments in your labs. But when it becomes a massive gauge boson, there is a third polarization, which is the longitudinal polarization, which is the polarization along the direction of the motion of the particle. And then if you consider that longitudinal polarization, you can look at the scattering of these bosons along this longitudinal polarization. Please do not confuse this L with the left right. Here this L means longitudinal polarization. Okay. So you can look at the scattering of these things of massive gauge bosons. Massive non-abelian bosons. Now, since the non-abelian gauge bosons have self-interactions, which we discussed, the triple gauge boson and the quartic gauge boson couplings, in this longitudinal polarization mode, now it will have couplings of this kind. It will have processes of this kind. This is a bit complicated to actually calculate, but if you have real good time, you can try to calculate this for a generic SU2, maybe even you can try it for the W boson, WL. So this is a WL going to a WL, going to a WL. And if you just try to calculate this process, you will see that the cross section, or at least the amplitude itself, goes like G square by 4 M square, because now you have made them massive, into S plus T. So you see the amplitude grows with S plus T. So if you square it, it will grow like S square plus T square. So this will start violating unitarity. So actually it will start violating unitarity at around 3 TeV or below. Okay. And actually this was a very crucial calculation that we knew, that we knew from the Fermi theory of weak interaction that the gauge bosons are massive, and we knew from this initial attempt at the gauge theory that it was a non-abelian gauge theory. So we needed a massive non-abelian gauge theory, and if we just added a mass term, the gauge invariance wouldn't be a problem. The problem would be that at around 3 TeV, this theory would stop making sense. So the assumption was that something has to show up before 3 TeV, before this famous terascale, to save the standard model from stop making sense. And the way it works is what is known as spontaneous symmetry breaking, or the Higgs mechanism. And we were so confident, and the community was so confident, that they kind of pledged around, I don't know what it is, around 5 billion US dollars on the LHC. So one of the major reasons that the LHC was built was to study this electroweak symmetry breaking below 3 TeV to figure out what is it that kind of protects unitarity below 3 TeV. And today we know that it is the Higgs. Okay. So let me take 10 more minutes before we take a break. So we have to now understand, if we cannot just add a mass term to this Lagrangian, what is the way forward and what can be done to, give a mass term that would still keep unitarity. And this is the idea of spontaneous symmetry breaking and Higgs mechanism. So the idea is very simple, that if you have any, first let me try to discuss what is spontaneous symmetry breaking. So if you have any quantum system, and it has a symmetry, and it has, that symmetry is, let's say, satisfied by the Hamiltonian of the system, but it is not satisfied or is not a symmetry of the vacuum configuration, then we say that that symmetry is spontaneously broken. Okay. So it is a symmetry of the Hamiltonian or the Lagrangian of the system, but not a symmetry of the vacuum configuration. And the Goldstone theorem tells us that this thing would mean that there would be some massless degrees of freedom. So let me briefly discuss what is this Goldstone theorem, okay? Very, very quickly. So let's say there is some quantum system given by this Hamiltonian H and a vacuum given by O. Of course, what it means is that H of O is 0. Okay, this is the meaning of that it's the vacuum configuration. Now, let there be some symmetry of the Hamiltonian, and it is, let's say, generated by a charge Q. Which, of course, if you know the Noether's theorem, can be written as some d4k of some 0th component of some current, right? Some Noether's current, where J mu x comma t is the Noether's current. I hope all of you know the Noether's theorem. So because Q is a symmetry of the Hamiltonian, what we can say is a generator of a symmetry of the Hamiltonian. What we can say is that Q, this commutation relationship between Q and H is 0. This is just definition that Q is a symmetry generator, right? And the symmetry transformation can always be written as e to the power of I theta q, right? This is the transformation. But if it is spontaneous symmetry breaking, for spontaneous symmetry breaking, we know that this transformation will not work on the vacuum. So this T acting on the vacuum will not take you to another vacuum configuration. So if you just expand this out, write it as 1 plus theta q, acting on vacuum, not equal to vacuum, and so on and so forth, this will immediately tell you that this Q acting on this vacuum is not zero. It is some non-trivial state, right? So you want to find out what is the energy of this non-trivial state, Q acting on vacuum. If it is not zero, it must be some state in this Hilbert space. So you try to figure that out. So you find what is H, Q acting on this. But this thing you can always write as H, Q, 0, and you can add a 0 to it, Q, H times 0. Remember, this thing is just 0 by our first term. So you have added a 0 to your right hand side. And what this is this is just H comma Q acting on 0. And so this is 0. So you have a very strange situation. The state that you have over here, not vacuum, 0 energy state. Now what is interesting is the following, that now you can define a new thing called G, which we call d4x e to the power of ipx, the vector part, times j0 times this. So G is a new state, right? Why this is interesting is that at, or let's say as P goes to 0, what happens to G? G just becomes d4x e to the power of I 0x j0 of 0, but this entire thing is just Q, so Q times 0, but this is a state which we just saw as E is equal to 0, energy 0. So G is a state where as P goes to 0, E goes to 0, so it's a 0 mass state. Remember, for any state, if the energy goes to 0, as the momentum goes to 0, it must be a 0 mass state. So this quick calculation that I have done, you can go through this calculation, you will find it anywhere, maybe even on Wikipedia or anywhere else. What I have just said is the following, that if you have a system, any quantum system, where there is a symmetry generator, which is a good symmetry of the Hamiltonian, but it generates a transformation which is not a good symmetry of the vacuum, for every such charge, there will be a corresponding 0 mass state. And this is the statement of the Goldstone theorem. Okay. So spontaneous symmetry breaking is this kind of a mechanism by which there is a symmetry of the Hamiltonian or of the Lagrangian satisfied everywhere, but not in the vacuum. And what Goldstone theorem is telling us, that every time this happens, there will be a massless state that will appear. And why this is useful is that the Higgs mechanism can use this massless state to make the gauge bosons massive, keeping unitarity. Okay, so this is spontaneous symmetry breaking plus Higgs mechanism. So I will take 5 more minutes. Do I have 5 minutes or should I stop now?
Yes, you can take 5 minutes if the participants are okay. Yeah,
Okay.
yeah, they are saying it is fine. So yes,
Okay, I will take 5 minutes.
okay.
So all this thing, what I've written, what I've discussed for the spontaneous symmetry breaking is in an abstract sense. So let me quickly try to point this out in a field theoretic context, okay? And discuss this for the abelian Higgs mechanism. So let's just think about a very, very simple Lagrangian of a kind where you have, let's say, a complex scalar field. So you introduce a complex scalar field, which has, of course, a real part and an imaginary part. Phi of x is alpha of x plus I beta of x. And you write down the typical Lagrangian for it. And along with it, you try to write down a potential for this thing, which of course, because it has to be real, it has to be a function of phi dagger phi. Now this potential phi dagger phi, typically, sorry, usually the potential has a minus sign. So can be the most common version is that you take phi dagger phi plus lambda square by 2 phi dagger phi whole square, something like this. And how does this potential look like? It has a very typical structure. So if I try to draw it, oh, what did I do? Very sorry. It will have this kind of a potential will look like this. So this is like phi mod, this is d of phi, and this is the minima of the potential. Right. But what if I take this potential and I put a negative sign in front of the mass term, and then try to do the same thing, try to check how the potential would look like. Now, if you draw the potential, it will have this. I'm sorry for my drawing capabilities, but it will look something like this. So it will have, of course, this symmetry everywhere, except it will also have this minima. It will now have a vacuum, what we call a vacuum manifold. So if you just minimize this potential, you can find out that the minima manifold is basically given by m square by lambda square. This is the equation for the vacuum manifold. So this is how it would look like. And you see, there's a symmetry in this potential that if you shift phi to phi prime, which is equal to e to the power of I theta phi, the Lagrangian does not change, right? So this is an global U1 symmetry. A priori, and that means anywhere along this, as you rotate this along the, this V axis or whatever you want to call it, nothing changes. A priori, also for the, this vacuum manifold in this case B, you can, there is a vacuum everywhere on this manifold. And therefore, the manifold itself is also invariant under the same phase rotation as you rotate it. So a priori, there is no problem. So this symmetry looks like it is getting protected everywhere. But the problem is that these points are separated by field space, in field space. And you cannot choose a minima which is separated in field space because of what is known as bulk effect or volume effect. You have to choose a minima which is localized in the field point, in a field space, like a minima over here, which is at one point in the field space. There's no bulk effect over here. There's one point in the field space. Here, if you want to protect this U1 global symmetry, you have to choose a linear superposition of every point along this minima, right? Every point along this minima. Quantum mechanics does not stop you. You can take a linear superposition of every point along that manifold and say that is your vacuum. And then your U1 global symmetry would still be satisfied even in the vacuum. But the problem is, then you are superposing different points which are separated in the field space. So it so happens that what is known as this, bulk effect or volume effect forces you to choose a specific field point as minima. So as soon as you choose one point as your minima, let's say you choose this point, immediately this U1 global symmetry is lost at the vacuum configuration. Everywhere else that still remains, but at the minima it is lost. Everywhere else in the Lagrangian it still remains. You don't need to choose. But for the minima, you need to choose. So what happens now is that you have to choose your field and expand it around that minima. So the way you do this is that you choose your field something like this, V plus H of X, e to the power of minus I G of X plus V, which is basically a polar decomposition of the field. Previously, I wrote it as alpha plus I beta. Here, I'm writing it in terms of this polar decomposition. And I leave it to you that if you now plug this thing into the original Lagrangian, you will see that you will get, of course, a typical kinetic term for the H field, which is, of course, now a real scalar field. You will get a very interesting kind of a kinetic term for this, this GX field, which looks like this. Something like this. Then you will get a mass term then you will get a potential which looks like this. So the potential, if you plug everything in, would look like this. And the important thing is that you will get kinetic terms and all this, but you will see no mass for G of X. And H of X is massive Okay. So you get one massless degree of freedom and one massive degree of freedom, just like what Goldstone's theorem predicted. Because one of your symmetry, global symmetry, U1 global symmetry, has been spontaneously broken by this choice in the vacuum, and you end up getting one massless degree of freedom. And now I will show, after taking maybe 10 minutes of break, that what you can do with this massless degree of freedom is that you can make one of the gauge bosons massive in a way that will not break any unitarity. Okay. So let us take 10 minutes break, and we come back and meet around 4:40. If there are any questions, you can go ahead, and the rest can leave as they wish. Okay. Are there any questions or comments? Okay, I think there are no questions, so I will stop sharing, and then maybe we'll start at 4:40. Is that fine for all of you? Okay, so I'm stop presenting now. Okay, so am I audible to all of you? Hello, am I audible?
Yes, sir.
Okay. Okay, so are there any questions regarding what we have discussed so far? I'm sorry that I have to rush through so much, but it's not easy to discuss the standard model in 4 hours. So I have to rush through these things. I hope you take away some of it, and maybe you can read up the rest of it from you know any standard textbook like Peshkin or Polashpal or somewhere else. But in any case, if you have some question, please let me know. Uh, okay, if not, with your permission, I will try to argue as to why this getting one massless scalar field, which we knew would come because of this spontaneous symmetry breaking, and one massive together, this combination is very useful, and how this is connected with giving a mass, protecting unitarity. Okay. Now, again, maybe if you get lost in all the mathematics of it, let me tell you the story. What will happen is that if you go back into this abelian thing where we discussed the problem, you see over here what the problem was, that in order to give this gauge invariant mass, what you needed, on one hand, you needed all these fields, right? These new things which we are calling the auxiliary fields. And we will see that this massless things that we are getting, which we are sometimes called the Goldstone bosons, those massless scalar fields or the Goldstone bosons, will provide you with all of these BAs, which would appear in these exponents. Okay. And they will give you the masses of the gauge bosons in a gauge invariant way. And that is nothing, this is exactly what we had over here. So the masses will come and the gauge invariance will be preserved. But the problem that we were having previously was with this unitarity. That we had these processes which was growing uncontrollably with scale and violating unitarity around 3T. Now, what happens in this Higgs mechanism, and which is the important crux, is that along with these auxiliary fields, the Goldstone bosons, you get the physical Higgs, which remains the massive part of that scalar field, which will remain in the spectrum. And those massive scalars will contribute to this WW scattering processes and many, many other things, but in also this WW scattering processes. And the contribution of that physical Higgs to this WW scattering process will be exactly such that it will modulate the growth of the cross section such that unitarity is never violated at all scales. Okay. So this is basically how the Higgs mechanism and spontaneous symmetry breaking and Higgs mechanism together solves this problem. So the Goldstone mode will provide the goldstones, in this case, which is this G of H, and you can already see that it appears in the exponent. Of course, this is the abelian case, that's why the generator is not there. And this will be responsible for the gauge invariant masses. But then, together with G of H, there is this H of X, which would, again, in the non-abelian case, would behave like a Higgs field, And this h of x would be the main thing that will modulate unitarity. Okay, this is the story, but let me just do the mathematics. So first, let me try to show you that the mass will be generated. I'm telling you the story, but how do we know that mass is generated? So that mass generation part, we can continue in this abelian Higgs itself. So all that you have to do is that instead of this, free Higgs, free Lagrangian, we move to an gauged Lagrangian. Okay, we know that this has a global U1, so we just look at a local U1 theory. So the local U1 theory with spontaneous symmetry breaking, and that would just be the Lagrangian like the previous one with instead of d mu, you will have just a del mu, right? Sorry, instead of a del mu, we will have a d mu. And then, just like previously, you will have this potential pi dagger phi, and now because it's a gauge theory, you need to put this kinetic term f mu nu, where you know, of course, that d mu is given by del mu minus I some g a mu. F mu nu is just del mu a nu minus del mu a mu. And this v phi dagger phi, we choose the one which leads to spontaneous symmetry breaking, which has a negative mass term, plus lambda square by 2 pi dagger phi whole square, for which we have already studied that the vacuum manifold is given by m square by lambda square, which is sometimes also called v square. In which case, it is better to write the field around this, expand this field around this vacuum state so that you can do the quantum fluctuation around the vacuum. That is always the idea, that your fields should be expanded around the vacuum. So you write it in this form, and you do this polar decomposition of a complex scalar field. You can always do that. Previously, the polar decomposition was difficult because you didn't have a mass scale, but now you have this V. And then if you write it down, then from the kinetic term, which was given by del mu phi d mu or whatever, d mu phi dagger, from this, one of the terms inside this, of course, would be the d mu 1 by root 2 v plus h, when the d mu acts on this, right? So we will have a d mu 1 by root 2 v plus h of x dagger. And again, if you write down all the terms from here, expanding the values of d mu, from d mu you have this minus ig a mu term. So if you pick up the a mu terms from both sides, you will get this minus ig by root 2 a mu v into minus ig a mu v by root 2 dagger, and that would give you a term which goes like g square by 2 v square a mu, which is basically half ma square a mu, right? Which is exactly like a mass term of a gauge boson. So at least the first part, I've been able to show that if you have a spontaneous symmetry breaking in a local U1 theory, the important steps are that, of course, because there is spontaneous symmetry breaking, your scalar field will have a non-zero vacuum expectation value, and therefore you have to expand the field, the quantum field around that vacuum. And once you do that, your gauge field will now develop a mass term. And that mass term, of course, will depend on the vacuum expectation value. MA will depend on G times V or something like that. Okay. So this is the same story that we have to now repeat for our, you know, weak Lagrangian. Where was it? So the weak Lagrangian that we initially wrote down is here. And we have to somehow provide a mass to these fields W mu by this spontaneous symmetry breaking mechanism. And the way to do this is that we know that we have to spontaneously break some symmetries. And the symmetry here is, of course, an SU2L symmetry. So we need an SU2L, a scalar field which will somehow be non-trivially charged under this SU2L, and that will break this SU2 to something so that some of these W bosons get massive. So we know that the scalar part of this theory should be such that it should be at least a doublet of this SU2. It should be charged under SU2 cross U1y. Okay, so we can try to attempt and write down a theory for the masses of the standard model weak gauge bosons. So what we'll do is that we'll invent a scalar field which will be charged and which will be a doublet. So there will be two complex scalar fields, which will be a doublet and which will have to have some hypercharge. Let's call it Y5. So it's a complex doublet under SU2L with Y5 hypercharge under U1y. So this is sometimes represented just by this thing that it is a doublet and Y5 representation, 2, Y5. So we write down, just like before, a free Lagrangian, which is del mu pi dagger del mu phi minus this dagger pi. And from our previous experience for the abelian case, this thing has to spontaneously break some symmetry. So we choose a minus mu square pi dagger pi minus lambda square by 2 pi phi dagger whole square. Now you have to check what are the symmetries that are there of this Lagrangian and what is spontaneously broken. So if you really think about it, this guy, this phi1, phi2, this big capital phi, has actually 4 components, right? This phi is something like this: phi1 real plus I, phi1 imaginary, right? And then it has phi2 real plus I, phi2 imaginary. So in reality, it has 4 degrees of freedom, and the vacuum manifold means that it has the whole thing is invariant and under any direction in this phi1 real, phi1 imaginary, phi2 real, phi2 imaginary. Just like previously, because we had 2 quantities, this alpha beta, everything was invariant under any direction in alpha beta. Now, because of this 4-fold symmetry, it could be invariant under any of these 4 directions. So basically, it has a global SO4 symmetry. which means that, which is of course equivalent, if you know your group theory, to an SU2 cross SU2 symmetry. Okay, there's SU2 cross SU2 by Z2, but let's forget about the Z2 for now. It's very crucial, but let's forget about it. So there's a SO4 symmetry in this Lagrangian. An easy way to think about this is that now the vacuum expectation value, for example, in this case, in the abelian Higgs case, this vacuum, you could have chosen it along the real axis, or you could have chosen it along the imaginary axis. So you could have chosen the vacuum expectation value to be along alpha, or you could have chosen the vacuum expectation value along beta. There was a twofold symmetry. The way we chose it was the vacuum expectation value was purely in the real direction. That's why V plus H is the real component, and the imaginary part went into the exponent. So we chose the real axis to be the direction of the vacuum. So in this case, there is 4 choices, and you could put the vacuum anywhere. You could put it along the real axis on the front, on the first row, or the imaginary direction of the first row, or the real direction on the second row, or the imaginary direction of the second row. So you have a 4-fold symmetry that you could have chosen. But you have to choose something. So the way you choose it, because of that spontaneous symmetry breaking, is that you choose everything in a way that you put the vacuum expectation value along the real axis in the second row. So you put it like 0 plus V plus H of X. You choose like this. And everything else, so the other 3, the real in the first row, the imaginary in the first row, and the imaginary in the second row, you put it in the exponents. These are the broken directions. Okay. And this breaking that you have over here is breaking this SU2 cross SU2 to an SU2V. So this is like an SU2L cross SU2R broken to an SU2V. This, you still, even after this this is the spontaneous symmetry breaking that has taken place. Previously, you had an SU2 cross SU2. Now you have broken to SU2V. So if you count the number of generators, SU2 has 3 generators. This SU3 had 3 generators. Now the unbroken part has only 3. So overall, you have 3 generators. Three spontaneously symmetry broken generators, which by Goldstone theorem, as we have discussed, for every broken generator, produces a massless Goldstone boson. Okay. But we started with 4 degrees of freedom. So there's one surviving degree of freedom, which is over here, which is the surviving Higgs field. So this is how the scalar sector would look like. You would start with this doublet structure. You would introduce this kind of a spontaneous symmetry breaking potential that would have a non-zero vacuum manifold. That manifold, the vacuum manifold, will have an SO4 global symmetry. But as we have just said, you are not allowed to choose a superposition vacuum which is separated in the field space because of the bulk effect or the volume effect. You are forced to choose one point in the field space So you have to choose somewhere. The one that you choose is along the real axis, what I call phi 2r. Real axis along the second row. As soon as you do that choice, your SO4 global symmetry is broken, and that breaking happens in a very specific way. This SO4 is isomorphic to SU12 cross SU2R by Z2. Forget about this Z2. The SU12 cross SU2R is now spontaneously broken to an SU2V. And that means the original 6 generators, out of them only 3 remains and 3 is spontaneously broken. The 3 that is spontaneously broken leads by Goldstone theorem to 3 massless degrees of freedom, which are given by this GAs. Okay, these Goldstone bosons which are massless. And then there will be one more, which is the surviving Higgs field, which we know is massive. So we'll come back to this surviving SU2V and what is its role very soon. But for now, let's continue with what we want to do. We want to just look at the masses of the gauge boson. See, from our previous experience, you see, if we are only interested in the mass of the gauge boson, we have to just look at the kinetic term, and that to the part where there is the coupling between the, the wave with the vector fields. So if we want to just be interested in the masses of the weak gauge bosons, we don't need to write everything down. That's a very messy job. It will take a lot of time. Let us just focus on the mass term. And that will come if we forget about everything else and just write down the part which comes from the masses of it, which means you take this half coming from the 2 1 by root 2s, then 0v, which comes from the the d mu dagger part, and then over here you will get okay one another, I think, half. Just give me a second. Let me try to figure this out. Yes, I by 2, because that is the sigma by 2. Okay, maybe I should write it out a little bit more for all of you to follow. Okay, so this will come from the where is it? D mu psi dagger d mu psi. Right, it will come from this term. So among other things, the mass term will come from this term, which in turn you can write this as del mu plus I G2 sigma A by 2 W mu A. This is the generator for the SU2 plus I G1 Y phi B mu. So this is the whole D mu acting on phi, whole dagger, and then this entire thing repeated. Del mu plus I G2 sigma A by 2 W mu A plus I G1 Y phi B mu acting on phi, right? So for this, what we would take is only, we'll replace the phi by the wave. We'll not take the d mu part, and we'll just take the part which is relevant. So the wave part is 1 by root 2 0v and then I by 2 G2 sigma A W mu A plus I G1 Y phi B mu into minus I by 2 G2 sigma A W mu A plus I G1 Y phi V2 into 0 V. Okay, I'm just writing it out. So if you now remember your sigma matrices, you can calculate this thing a little bit more explicitly. It happens to be something like this: 1 by 2. There's a 1 by root 2. Sorry, there's another 1 by root 2 over here. So we can take this 1 by root 2, 1 by root 2 out. So it's half, then a half and another half. So 1 by 8. I think we can put this whole 1 by 8 over here. Then 0 V. And then this matrix that you would get is G2 W mu 3 plus G1 Y phi B mu G2 W mu 1 minus I W mu 2 G2 W mu 1 plus I W mu 2 minus G2 W mu 3 plus G1 Y phi B mu. Into this same thing again. G2 W mu 3 plus G1 Y phi B mu G2 W mu 1 minus I W mu 2 G2 W mu. So now everything is upstairs. Okay, so this is what I missed last time. Please be careful about into 0 times V. Okay, so you see this is a very, very messy calculation. You can do this. The important things are, okay, just let me correct one thing. So this second term, all the mu's should be upstairs, okay, over here. Don't get worried. This is just some algebra. There's nothing in it. There's no conceptual thing. You have to just do matrix multiplication. Now you have to do some identification. So the identifications are the following. This thing that you have over here is usually identified as 1 by root 2 into omega mu minus. And what you have over here is identified, sorry, not 1 by root 2, root 2 times that. Okay? Root 2 times that. Root 2 times omega mu plus. You have to make this identification. And what you have to identify is that what you have over here, including that minus term, let me put that minus term inside, including that minus term, and let me write it a little bit better. This entire thing is defined as G square, and that is G2 square plus G1 square Y phi square whole root times minus of Z mu. So this is what you have to identify. Okay. So if you make those identification, this matrix simplifies a little bit. that this mammoth thing that you have over there becomes like 1 by 8, 0 times V, and then the matrix becomes whatever is the first term. I couldn't care, because you see there's a 0V and 0V. The first term will never give anything. Then the first off diagonal term is root 2 W mu plus and root 2 W mu minus times this quantity. Let me call it by this symbol, just this root. So root times Z mu minus root times Z mu multiplied by whatever is here into root 2 W mu plus root 2 W mu minus into minus of Z mu. So again, the first term, everything is upstairs, sorry. And multiplied by 0V. So I leave it to you to do this multiplication, and you should be able to show by just doing simple multiplication that what you would get if you do this multiplication is the following. You would be able to show that you get something like G2 V2 whole square W mu plus W mu minus. You get one term like this, and then you get one more term which goes like 1/2 into W, sorry, half of G2 V2 whole square divided by what I'm calling cos square theta W times Z mu Z mu. Now what is this cos square theta W? Let me just now tell you what I have what we called as Z mu. See, this thing that I defined as Z mu is from our definition over here was given by this expression, right? Okay, where was it? This G1 Wi-Fi B mu is equal to given by minus G1 Wi-Fi B mu plus G2 W mu 3 whole divided by G1's Wi-Fi whole square plus G2 whole square whole root. Something like this. It's a linear combination of this B mu and omega mu 3. Now this thing, if you want to write it nicely, can always be written as some cos theta times W mu 3 plus minus sine theta W of B mu. Okay. And then you can check that this cos theta W comes out to be G2 by this G1 Wi-Fi whole square whole root. And sine theta W comes out to be G1 Wi-Fi divided by this same thing. So these are what are called the Weinberg mixing angle. And the important point is that you can define this Z2, Z mu boson as some kind of a linear combination of the W mu 3 and the B mu gauge bosons. And if you do that, then you see that the masses that you get is for this Z mu guy and the W mu. And you can even put it more nicely if you rewrite that mass term a little bit more. You can write that as mw square W mu plus W mu minus, and the second term, if you put it nicely, basically comes out to be mw square by cos square theta W times Z mu Z mu. And where Z mu is this combination of W mu and B mu. But then you will ask, what about the orthogonal combination of W mu and B mu? You are very within your rights to now define another field, A mu, which you define as the orthogonal combination, because if you have two fields, you can have two possible combination, which is given by the cos theta W of B mu plus sine theta W of omega mu 3. This would be the orthogonal combination to Z mu, and you will see that this field does not show up in your mass term, so which indicates that this field exists, but this field has possibly zero mass term. So in the end, what you find is what you wanted. Your W and Z bosons are your weak interaction gauge bosons, which are now massive. And in addition to that, you have a new thing, which is a massless gauge boson, which is this A mu. And this will give you your usual electromagnetic interaction. Okay. The only trick here is that this Z and A are not pure part of the SU2 and the U1 that you started with. It so happens that the W plus and the W minus are pure SU2L part. But the Z and the A is a linear combination which mixes the SU2 with the hypercharge. Okay. So in the end, you get these two parts of it. One is this part, which is responsible for weak interaction. I don't know what happened. Okay. Let's just do like this. So there is this part which is responsible for weak interaction. And then there is this part which is responsible for electromagnetic interaction. Okay. And there is also prediction now. The prediction is that for the weak interaction, the two bosons that you have, the two vector bosons that you have, W and Z, the masses of those two things are not independent of each other. The masses are actually related to each other. The mw square by mz square and this weak mixing angle cos square theta W, they are actually equal to each other. So the masses of W and Z bosons of weak interaction are related, and this is sometimes known as the rho parameter. And the standard model tells you that this rho parameter should be 1. And if you want to know that why is this, that why are these two different gauge bosons, each of them could have their independent masses, but why they are correlated to each other, why their masses are kind of similar. If they are not exactly equal, they are related by this small mixing angle cos square theta W. The reason is that you see, when you were breaking this spontaneously, this symmetry, you could not break all of the global symmetry. Certain amount of symmetry remained. This SU2V symmetry still remained. This SU2V symmetry is called the custodial symmetry. So the SU2V custodial symmetry treats this W mu 1, W mu 2, and W mu 3 on equal footing. So if the custodial symmetry, which remained after spontaneous symmetry breaking, was exact, the consequence would have been even more, that MW would have been exactly equal to MZ. But what happens is that even this custodial symmetry does not remain exact. Even after spontaneous symmetry breaking, something more happens. And this is called the hypercharge mixing. Because this U1Y now still mixes through this small angle cos theta W with this custodial remaining global symmetry, custodial symmetry. Even after spontaneous symmetry breaking, there was a symmetry that was remaining in the Higgs sector. But that, because of this hypercharge mixing, even that is broken, which is why instead of this direct relationship, now we have this new relationship that mz square is mw square, sorry, the other way around, mw square is mz square cos square theta w. Okay. So now, with everything put in place, it is straightforward to do one more thing that is left. See, we have to now figure out, we now know what the masses are, everything is, but still we have to figure out what this YL and Y phi is and YR is. Because these hypercharges that we have introduced is still undetermined, right? So we have to know what these hypercharges are. So in order to figure out what those hypercharges are, we have to now go back and look at the interactions. See, we had introduced this thing called Wi-Fi, YL, and YR. So we need to know what these values are. Because after all, Wi-Fi, YL, and YR is something are charged under U1Y, which you cannot go out and measure in an experiment. So you have to somehow fix them. What is a doublet and what is a singlet is clear. But what is Wi-Fi, YL, YR is still unclear. So in order to do that, you just look at the weak interactions for the leptonic sector. You remember it is just given by I gamma mu L, and I'm just looking at the interaction now and nothing else. And I'm not even writing down the family index anymore, because what am I doing? Where is my DLR and DR mu? This is something that I wrote down before the interval. Okay. So you have to just write down what these things are. So what is DL and DR? I've already introduced, except that now you have to write it in terms of the matrix. So if you just be careful for only any one generation, let's say we do it for the electrons, you can do it for whatever you want. It becomes something like this, I by 2. Again, the same thing that we did before, G2 omega mu 3 plus, but now Y will come is with YL. Remember, here when we were writing down these matrices, it came with Y phi, because that is what the covariant derivative of the phi was. But now it is the covariant derivative for L, so it will come with YL. G1 B mu 3 This thing is still root 2 G2 omega mu plus. This is still root 2 G2 omega mu minus, and this is minus G2 omega mu 3 plus YL G1 B mu 3. And the whole thing has to be multiplied by mu E on the right hand side. So this is the first term, and the second term is relatively easy because it only has hypercharge interactions and no SU2 interactions. What you have to be careful is that you see, you can no longer interpret what you have over here as Z mu, because in the definition of Z mu, you needed to have Y phi over here, and what you have over here is YL. So this is not Z mu anymore. So you have to use the reverse, transformation matrix transformation. So you define Z mu and A mu like this by this equation. So you can inverse this and write down what is B mu and W mu 3 in terms of A mu and Z mu, right? It's just reversing this equation. So you can just use, for example, the fact that you can write W mu 3 as cos theta W Z mu plus sin theta W A mu. This is just the reverse of that. And B mu 3 as cos theta W A mu minus sin theta W Z mu. Okay. So you just replace this in these matrices and figure out interaction by interaction. So I will not go through everything, it's impossible, but I leave it to you as a homework. You can look at what is the interaction between mu E and mu E. Okay. And figure out what is the interaction of mu E and mu E with A mu. And if you do that, if you collect, if you just do the multiplication over here, mu E with A mu alone, by replacing everything, you should be able to show that this mu E coupling is something like this: mu E gamma mu by 2 G2 sin theta W plus YL G1 cos theta W mu E A mu. Now you see, what is this coupling? This is a coupling of neutrino with a photon, what we want to say an electromagnetic coupling. But we know that the neutrino is chargeless. So the neutrino should not couple to the photon. So from this, we should come to the conclusion that something like G2 sin theta W plus YL G1 cos theta W should be equal to 0. And then if you again use the definition of, where was it? Somewhere we introduced the cos theta W. The Weinberg angles, the sin theta W and the cos theta W. If you just plug it in over here, you should be able to show that what this means is that Y phi plus YL should be equal to 0. Okay. Similarly, if you use the coupling between YR, ER and ER, you will be able to show, and with A mu, again, you should be able to show that this coupling is given by ER bar, I, gamma mu, YR, G1, cos theta W, ER, A mu. This is very easy to show, right? Because the coupling is here only with B mu, so you have to just replace, there's no B mu 3. I'm very sorry, sometimes I'm being sloppy. So B mu, the A mu part is just cos theta W A mu. So you just replace the a mu with cos theta w a mu. So you get this a mu cos theta w for the a mu part. So this coupling is the right-handed electron coupling with photons. But when the photon couples with the electron, it doesn't care whether it's coupling with the right-handed part or the left-handed part. It's just QED. So it couples with an electron with its electric charge. So it tells you that this entire thing YR G1 cos theta W should be the electric charge minus E, or maybe there is so many E, so let me write QE, which will tell you that it is the electric charge. Okay. So the way to match this is by assuming that YR is -1 and G1 cos theta W is the electric charge itself. And finally, you can even look at what is the coupling of EL and EL. And again, you would like to look at what is the coupling with A mu. And you will see that this coupling comes out to be EL bar by 2 gamma mu A mu EL, and then the coefficient happens to be minus G2 sine theta W plus YL V1 cos theta W. And again, this coupling, just like the right-handed coupling, the left-handed coupling should also be equal to, minus QE, right? So if you plug in the values of, cos theta W and sine theta W, what you will find that what this expression is telling you is that G1 times G2 times this entire root or whatever, this is G1 cos theta W, right? What this is telling you is G1 cos theta W times minus Y5 plus YL is equal to minus QE. Okay. And then if you just solve this, because you already know that this thing is just QE from our previous ER study, you now have another equation that minus Y5 plus YL is equal to -1. So you have two equations. This is 1, this is 2, and you simultaneously solve for Y5 and YL. So from 1 and 2, you can now show that the only possible solution is that YL is equal to -half and Y5 is equal to half. So you have fixed all the things by looking at the interactions. So once this is done, basically you are now ready to write down the electroweak Lagrangian for the leptons. So let me just write this down once for all of you. Remember, what are the fields? The fields are given by these things: mu E, E, L, mu mu, mu L, and mu tau, tau L. These have representation which are doublet under SU2. And now we know that its hypercharge is given by -half. So it's given by -half over here. So this is the representation under SU2 cross U1 Ly, right? And then you have the E fields, which are given by the ER, mu R, and tau R, and its representation is 1. And we just figured out that YR is -1. So its representation is -1. And then you need to have, of course, the scalar field phi, which is given by 0, V plus H e to the power of minus sigma A broken G A by V, which has a representation of 2 comma half. And now, if you try to write down all the possible things that you can do with this, these things, you get the Lagrangian for weak interaction. First, you have, of course, sum overall family, L of F bar, I gamma mu, d mu L of F, plus E of F bar, I gamma mu, d mu R E. This is the kinetic term for all the leptonic states. Then you have the kinetic term for the scalar sector. And the spontaneous symmetry breaking potential that you need, which we have discussed. But in addition to all this, and this is the interesting thing, but once you put the scalar and all these fermions together, you can write down one more interesting piece, which can be written like this: YE of F L bar pi E plus Hermitian conjugate. So this is the new term you can write, and you can check that this term that I've written is also invariant under all the symmetries. Of course, it is invariant under the Lorentz symmetry because it has a fermion antifermion. It is invariant under SU2 because it has a 2 bar and a 2. It is invariant under the hypercharge because you can add all the hypercharges and you can see it is 0. So this new term is invariant under everything, and this new term is called an Yukawa term. Okay. And why this is interesting will come later on. And then for completeness, let me just write down what all this d mu L things are. This is d mu minus I G2 TA W mu A minus I G1 YL B mu d mu R is equal to del mu minus I G1 YR B mu, and d mu phi is equal to del mu minus I G2 TA W mu A minus 1 I G1 Y phi B mu, where Y phi and YR are all given in these notations. And the only thing that you have to remember is that the W mu 3 can be written as cos theta W Z mu plus sin theta W A mu, and B mu can be written as cos theta W A mu minus sin theta W Z mu. And you want to write everything in terms of the B mu and Z mu, where tan theta W is given by G1 Y phi by G2. This is the definition of tan theta. So everything that you need is over here, except let me just discuss the Yukawa term just once more. Why it is interesting is that that thing you can write See, I wrote this thing. Just check once. See, this is a doublet bar, this is a doublet, and this is a 0. So this is an SU2L singlet. Let's look at the hypercharges. So the L bar has a +1, a +half. So this is +half. Pi is also +half, and E is -1. So you add them up, it is a zero hypercharge. And this is a fermion, antifermion, and a scalar. So this is a 0, 0 under Lorentz. So this is a Lorentz and gauge invariant term. Okay, so this is a legitimate term that you can write. I'm again suppressing the sum over families. There's sum over families, but every term would be, if one term in the family is gauge and Lorentz invariant, every term would. But why this is interesting? This is interesting because if you now think about what will happen to the wave term, see this Yukawa at the vacuum expectation value, how does it look like? So this term is like this. L bar has a new E, E, L, and there's of course a Hermitian conjugate to this. And then the vacuum expectation value is just given by 1 by root 2 times 0 V. And then there is a ER. So the term looks like this plus Hermitian conjugate. So if you multiply this thing overall, you get a YE times V by root 2 E. Okay, this is all bars. Sorry, I forgot the bars. So this is an EL bar ER plus Hermitian conjugate. So this term exactly looks like a mass term for the electron. Remember, in the chiral basis, the mass term has this EL bar ER plus Hermitian conjugate. And it gives a mass to the electron, but no mass to the corresponding neutrino. So we exactly recover the masses of all the leptons also through this mechanism. Okay. So given this, this is the entirety of the electroweak Lagrangian in the for the leptonic sector. Of course, the V phi dagger phi, is what we wrote down previously. I'm not writing it again. So let me just, wear it up. So if all the interactions and everything is a very messy part. You can, it's a very good exercise if you are learning the standard model for the first time, because it looks very compact. But if you just write it out, you will see many, 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 many terms just falling out of it. So you should, it's a good exercise if you have time to just write out every term in this Lagrangian. Maybe I should also write out what is this part, right? V phi dagger phi, if you remember, is minus mu square phi dagger phi plus lambda square by 2 phi dagger phi whole square. Now, if you want to do this same story for the quartz sector, you see, all that it matters now, because the scalar sector is same, for the, for the matter fields, for the, in this case, for all the fermions, all that you need to know are these charges, right? Once you know these charges, you can write down these covariant derivatives and whether or not you can write down the Yukawa terms. So if you want to repeat this entire story and you want to write down what is the electroweak Lagrangian for the quartz, all that you have to do is that you have to know what are the representation of the quarks under this Su2L cross U1Y. So I don't want to waste any time except telling you what those charges are, and I will leave it to you to construct the Lagrangian. So the electroweak interactions of the quarks. So the stories are same because parity is also violated. We know only the left component of the quarks will take part in electroweak interactions. And since again, if you look back into those Fermi theories, just like the electron and the electron neutrino was always coming in pairs, we know there's the weak isospin which keeps the up and down also in pairs. So you have the same doublet structure, left doublet structures. So all that you have to do is that now you have to invent this QL fields which will have the up and the down in the same doublet, but the left chiral components of it. You again have the three families of this same thing happening. The same thing happening. So under SU2 L cross U1Y, the charges that it will have is 2, comma. Now what this will be? You have to figure that out. Now, in order to figure that out, you go back and you check this minus half term. How did we get it? You see, one way we got it, of course, we did the exact calculation, but there was an easier way to do all of this. There was a formula for the charges of these fields. The formula for the charges was that, I should write it somewhere, that the charge formula was that Q is given by T3 plus Y. How? You see, if you look at mu E and E in this doublet, the T3 charges for this is plus half for this and minus half for this. And if we take the Y charge to be minus half for both of them, then the Q for this will become 0 and for this will become minus 1. And exactly that is what we want. Right? So the Y, the hypercharge that we were getting, and that is how we fixed, right? The way we fixed Y is by getting the right electric charges with photons, by getting the right interaction with photons, if you remember. So basically, we were trying to get the right electric charge. So the group theoretic way of doing this is basically we are trying to get the right T3, which is the generator of W mu 3 with Y. And we were trying to add them up to get the right signs like this. So we were basically, in a hidden way, using this simple formula. So now, we do the same thing. We know that the up quark has a charge of, let's try to do this. So the up quark has a charge of Q for up quark is 2 by 3, and this should equal to, T3 for that is half plus some Y. So you can immediately figure out Y is 2 by 3 minus half. And if you do this calculation, you will find this is 1/6. Okay. Then you have the right-handed components like you had previously. So you have the up-type right-handed components. So previously, you remember in our story for the leptons, we had only the right-handed components of the electron, but no right-handed components of the neutrinos because we assumed that the neutrinos are massless. But this we cannot do for the quarks. We know that both the up and the down are massive and all of them are massive. So we need right-handed components for all of them. So you have to have a UR, CR, and top R. And all of these things have to be not participate in the weak interactions. So this have to be or at least the charged weak interactions. So they have to be SU2L singlet. And then from that charge formula that we just discussed, you can figure out that its hypercharge has to be 2 by 3. Basically, in this case, the hypercharge has to be the charge. And then the down type dr has to be some dr, sr, and br. This also has to be a singlet, and its hypercharge has to be minus 1 by 3. And then you can just write down the full interaction for the quarks as before. It will be just QL bar I gamma mu d mu q of QL plus UR bar I gamma mu d mu u UR plus dr bar I gamma mu d mu d of dr, and you know how to construct this d mu and dd with these charge assignments that you have. And then what about the Yukawa terms? For the Yukawa terms, again, there will be this family index everywhere. There are 3 families of quarks as well. So you sum it up. For the Yukawa terms, for the down type Yukawa terms, it's very easy again. You have the QLF, YDF, pi times dr. Now the problem comes that if you want to give also something, a Yukawa term for the up type quarks, for that you need to write something like QLF bar. Instead of phi, you need to invent something called the phi tilde times UR, because the hypercharges are slightly different in this case. So you need to shift the hypercharges of the phi field to match the fact that the hypercharge is 0. So basically this phi tilde is given by this fully antisymmetric 2 cross 2 matrix epsilon times phi, which is given by 0, 1, minus 1, 0 times the original phi. This is a fully antisymmetric 2 cross 2 matrix. Remember, this has a representation of 2 comma half. Sorry, not this. The original Higgs has a representation of 2 comma half. Then this field has a representation of 2 comma minus half. And you can check that you need this 2 comma minus half to get the right 0 hypercharge over here, whereas you need this 2 comma minus half to get the right hypercharges over here by adding up the hypercharges from what we have figured out. And therefore, if you add this Lagrangian to the Lagrangian we have found previously, that gives us the full electroweak Lagrangian of standard model. And then if you add it to the QCD Lagrangian that we discussed at the beginning, that gives you the full standard model Lagrangian as a whole. And everything in standard model basically follows from these 3 pieces of the Lagrangian, and there's nothing else to it. Of course, there's some things which I'm hiding, or which we don't have time to go. Maybe I will just take 5 minutes, because it would be very unfair if I just write down this Lagrangian and never come back to tell you that what are the proof that this Lagrangian that I have written is actually experimentally verified. Okay, so I will just take 10 extra minutes to tell you that what are the experimental verification of the electroweak theory. So among many things, it has been verified again and again, always, But I think the most accurate verification of this electroweak theory that we just discussed came at the measurement at Z pole at LEP. Okay. So what is this? So, LEP was a collider experiment at CERN, which ran from 1989 or 1990 to 2000s or so, or maybe 2002 or something like that. And among many things, what it was, one of the main aim of this was to study this, thing where, E plus E minus uh, annihilated on the Z pole. So it was designed in such a way that the E plus E minus center of momentum energy was exactly or near the mass of the Z boson, that Z mu boson that we just discussed. Okay, so it would produce millions and millions of the Z boson, and then the Z boson would decay to many things, let's say to hadrons, okay, etc. So this event happened again and again and millions of times in this LEP experiment. The reason why this is one of the best verification of the standard model is because of the statistics of this thing that I've written is extremely unbelievably high at LEP. And this event has been studied to great accuracy at the LEP experiment. And I cannot emphasize the accuracy with which it has been studied. Okay. And what has been observed is are typical peaks like this, typical diagrams like this, where let's say you plot the center of mass energy with the this hadronic cross section of E plus E minus going to hadrons, and typically what you see is this Bright-Wigner peak. Okay, and this Bright-Wigner peak happens because of the propagator of the Z, this virtual Z, which I hope you know typically looks like this P minus Z square, minus I mz gamma Z whole mod square or something like this. So it looks like this, and this peak has been studied to great details. Now it gives you a wealth of information. For example, just from the location of the peak, where the peak happens, we have a very, very good determination of mz. Okay, so we know the value of mz to a very good accuracy. Then by knowing what is the width of this peak, we know what is the total decay width of Z boson to hadrons. So this is known to a very good accuracy. Then on top of that, since we know Z boson to hadrons, and it so happens, among the various hadrons, sometimes, what is hadrons? Of course, these are quarks, and then the quarks hadronizes. So it can, Z can go to, up bar. It can go to bottom bar. It can go to many, many things. It cannot go to top because the LEP energy was not enough to produce top, but it can go up to bottoms. Now the bottoms have this property that it has a slightly longer lifetime. So among the various quarks that it can go to, which then hadronizes, if it goes to a bottom and then it hadronizes, you can differentiate it between the hadrons. Okay, so you can differentiate whether before hadronization, whether it went to become an bottom and then an hadron, or whether it was just some other quark and an hadron. It is something that you can experimentally do. So people could measure something called this quantity called RB, which is the probability branching ratio of a Z going to a BB bar to the branching ratio of this Z going to any other hadron. So this was also experimentally measured very, very accurately, because Z was continuously decaying to hadrons, right? So we had a very good measurement of this thing. Then, among other things, sometimes, of course, the Z had an invisible decay. So it could also, the Z could sometimes decay to neutrinos. Okay, the electron neutrino, it could decay to other things. And typically what would happen is that if it was decaying to something, if it was decaying to more things, let's say, depending on what are the number of neutrinos we have, we never knew that we have 3 families. How do we know that there are 3 families and not 4, not 5, not 6? So Z can, if there are 5 families, Z could decay to 5 families. Now you can say that the massive guys are heavier, it cannot decay to them. But the corresponding neutrinos will always be lighter, and the Z will always be able to decay to them. So how are we confident that more or less there are 3 families, or at least 3 light families? The confidence comes from the fact that, you see, this is, let's say, the Z peak with assuming 3 neutrinos or 3 families, not electron neutrino, 3 neutrinos. That is electron neutrino, muon neutrino, tau neutrino. But let's say now if you have, okay, I have not drawn this well, so let me redraw this. Let's say this is what would happen if you have 3 family. If you had a 4 family, this is what you would expect. So the thing will become broader because the decay width would become more and the height would become lower. So this is what would happen with 4 neutrinos. So from the measurement of the decay width to neutrinos, which came out to be around 170 MeV, so these numbers I'm just putting in whole just neighborhood, we could figure out that the number of neutrinos in this universe is around 3. And therefore, the number of families is around 3. Other than this, other things that were measured were like this backward-forward asymmetry, which is the probability of Z, let's say, decaying to an purely left electron minus this decaying to a right electron. This has slightly different kinematic distributions. So from studying the kinematic distribution, you can differentiate between them. And from this was again very well studied. And if you, I think this is something that maybe you can discuss in the tutorial if you have time, or maybe on your own. You can show that this, to some approximation, is given by 1/4 minus sine square theta w. Okay. So once this is measured, this sine theta w was also measured. Then, of course, now if sine theta w is measured, mz is measured, sine theta w is measured, and mw was also measured. All measured. And finally, this rho parameter, which if you remember is given by mw square by mz square cos square theta w, this was also measured. And its deviation, you remember in the standard model prediction is 1, and the deviation from that 1, that delta rho, was found to be just 10 to the power minus 3 from experiment. So you see, so many things. I'm just writing a few. 1, 2, 3, 4, 5, 6, 7. These 7 things among many things were measured. And in each of these things which were measured, and not once, with huge statistics, millions of times in lab, whatever was measured in the experiment, it was found to exactly match what would come from the prediction of a of the standard model Lagrangian. It was so accurate that if you just take the tree level diagram, they were matching. People then said, okay, maybe it's matching at tree level. What happens if you take the loop and do the renormalization? And people found that if you do that carefully, it was even matching at the loop level. Okay, so this is what is known as the precision electroweak observables. So in some sense, the standard model is probably the most tested, uh, theoretical model in all of known to mankind. And so far, in every experiment that we have done, it seems to match what theory with experiment with hardly any anomaly anywhere, and which is a very good thing for standard model, but also something that we have to wonder that why something that was discovered nearly 50 years back is still holding up, whether we are experimenting the right parts or whether there is something else to look forward to. So I think that is a good place to stop. I don't have anything more to discuss because again, that would open up something new. So if there is any questions, otherwise we can just close this discussion on the standard model. Please feel free if you have any question.
Participants, yes, participants, if you have any question, please unmute yourself and you can discuss. Okay, I don't see any question.
Okay, so thank you. Should I
Let's
now
then,
stop sharing?
yes, yes, you can stop sharing. And I thank on behalf of the organizers, within a short span of time, we covered a lot of things. I'm sure those things will be very beneficial for the participants. And we look forward to see you in some future panel activities in person, if possible.
Sure, sure, sure. Thank you.
Okay.
Thank you. And I hope you have a very
So,
nice experience in this school, all of you. Best of luck with that. Uh, Thank you. So I'm disconnecting for now. Okay. Best of luck to all the students. And
okay, okay,
okay.
okay. Okay, so participants, today we are not going to conduct the tutorial. Tomorrow we'll have the tutorial on the standard model. Okay, so today's session is closed. And please give the feedback to every course so that this should be helpful for the future.